Hi, how are you doing? So if you're here for the deterministic L2 cache solution on performance in an AMP-capable SoC, you're actually in the correct place. I couldn't fit the title on the slide, so I had to come up with something else. So I'll start with a little bit of background. So I work for the Macrosemi FPGA business unit. So we've recently been acquired by Microchip, so hence Macrosemi, a microchip company. But in actual fact, our roots go back to a different company called Actel. And it's a company that used to service the defense and aerospace market. And we've kept quite a lot of the DNA from that company, which means that we have certain values that we work towards, which are things like high reliability, power, and security. So we've innovated with SoC FPGA a few years ago. So that turned out quite well, so well that everybody seems to actually follow the same recipe and replicate putting a microcontroller or microprocessor on the same die as an FPGA. So that gives our customers the ability to actually innovate with peripherals without having to create a complete subsystem. So I'm really going to talk about how RISC-V allowed us to innovate for our own requirements. So we've just announced the third generation of our SoC FPGAs. So previously, we had microcontroller-based FPGAs, but our customers have been demanding a rich OS. But at the same time as demanding a rich OS, they still want to have some of the real-time benefit that we provided with our previous generations. So we still want a rich OS like Linux, but they still want to keep safety critical and real-time system control as one of their main applications. So in order to do that and fulfill our customers' requirements, we've partnered with SiFive to come up with an architecture that would actually fulfill those requirements. When we were given the requirements for this device family, we were asked to do support real-time. So real-time is somewhat of a subjective concept. Depending on who you're asking, you'll get a different answer. So it turns out that there is actually one definition that I like and I think summarizes what real-time is really about. And it's basically a system able to control a physical process at a speed suitable to the process under control. So that gives a lot of leeway as to how real-time your real-time system is. But in actual fact, when you're talking about real-time, most of the time what you want is determinism. You want your system to behave the same way all the time, no matter what. So determinism is really the key nut to crack for this architecture. So we've put a lot of effort into achieving this. So starting from a standard application processor, what is really a standard application processor? What are its characteristics? The first one is the memory hierarchy. Typically, you have an L1 cache per core, per processor core, on top of which you're, sitting on top of an L2 cache, which is shared all of the processor cores. And then you have some microarchitecture performance enhancement features that allow you to run faster. And all of this is sitting on top of DDR4. So it turns out that that's not really friendly from the point of view of determinism. Because what actually happens is that memory hierarchy results in cache misses. And we cannot actually predict which way the cache misses are going to take place, when they're going to take place, and how many there's going to be. Likewise, in this architecture, we have a memory coherence interconnect, which is concerned with maintaining coherency of the memory across all of the different cores. So it doesn't really care about determinism. It does some magic there to operate as efficiently as possible, but there's nothing deterministic in that interconnect, even at that level of the memory. So when we actually try to execute some code on such an architecture and look at the execution time of interrupt service routines, we find that they tend to be all over the place. Here we have a graph that shows the execution time of an interrupt service routine over time. And we find that that same interrupt service routine doing the same job, depending when it's doing it, takes a completely different amount of time and is completely unpredictable. And this is what is really causing us trouble from the point of view of determinism, because we cannot fetch instructions or data deterministically from the memory hierarchy. So we went and tried to figure out how to fix that. We went back to the basics. So the basics in a real-time system is typically like a background and foreground loops. So you have your main application running in the background loop, which is interrupted by foreground tasks at regular intervals. How do we go and achieve that in a deterministic manner in our architecture? The answer there was somewhat simple, and like it's something that's been done before, is that we actually reuse the memories that we use for L1 cache on L2 cache and reconfigure them to be used as tightly coupled memory or tightly integrated memory. So this gives us a deterministic access time to those memories to actually fetch instructions or fetch data or write data. So we've actually modified the standard application class architecture by making those L1 caches and L2 caches configurable into scratch pads or tightly integrated memories. So that brought us quite a long way towards achieving determinism. When we rerun the same benchmark, we actually find that things become a lot more deterministic in the execution time of our interrupt service routines. But it's still not perfect. And at that stage, when we were looking at those graphs, we were not entirely sure what was happening. So my assumption at that stage, when we saw these graphs, was that we were doing things incorrectly in the way we were configuring our memories. So spent some time debugging the code, actually making use of the performance counters that were available in the architecture to try to figure out what was going on why we were getting this execution profile. And eventually figured out that there was a direct correlation between the number of branch mispredictions and the length of time that it took to actually execute the interrupt service routine. So at that point, that meant that we had to make some other changes to the microarchitecture. So here again, we engaged with our colleagues in Sci5, had a very interesting discussion with Krista, where we showed him the numbers that we were getting, and or suggestions of modifying the microarchitecture to give us the ability of dynamically disabling the branch predictor on entering and exiting critical section of code. So Krista was not actually entirely in love with the idea initially, but he was actually good enough to actually look at the numbers and listen to us and to actually understand our requirements. Went off, and one day after having the discussion, came back to us and said, actually, you know what, yes, we're actually going to make that change, and we'll give you a code drop next week. So we went again, reran the same benchmark, and lo and behold, the system is perfectly deterministic in that benchmark. So here we've actually achieved determinism in an application processor. So in this application profile, what we're actually trying to do is not to run Linux and make it deterministic, because as I said earlier, the real-time being a system able to control a physical process at a speed suitable to the process under control. If we had stopped at that definition, what we would have done is enable the preemptarity patch in Linux and be done with it. But when we actually looked at our customer requirements, we found that the unit they were giving us as part of requirements and use cases were not in milliseconds, but they were in clock cycles. And at that level, there's no way that we can do anything with Linux that will allow us to meet those requirements. So what we are proposing to do with this architecture is to actually run the real-time code on one of the cores where we only execute bare metal code or something executing under a real-time operating system, where we actually configure the L1 cache as a tightly integrated memory, and the L2 cache as a loosely integrated memory, giving us determinism, and then use the other cores to execute Linux. So that's what gives us the ability to provide microcontroller class determinism in a Linux environment by dedicating one of the cores to handle all of the real-time requirements. And some additional benefits to this architecture is the configurability of the L2 cache allows us to pin data structures into the L2 memory. That L2 memory, even when it's pinned, when we pin data structure to it, still remains coherent to the rest of the system. So we still have a cache coherent message passing system between the real-time context and the rich OS context. So in summary, working with our partners in Sci5, we've actually achieved the creation of an architecture that allows us to execute Linux, run Linux, and gives us access to an extensive software stack while still retaining the capabilities to handle hard real-time operations. Okay, thank you very much.